Previously, we used a switch network to represent the boost converter. And practically, we can use a pair of MOSFET and diode to implement this switch network in boost converter. But both MOSFET and diode, they have conduction loss. So next, we are going to introduce the semiconductor device's conduction loss to calculate boost converter's more accurate DC transformer model, such that we can more accurately derive the voltage gain and efficiency of the practical boost converter. So first, let's plot the schematic of boost converter with the practical semiconductor device. So again, we have the input source. Inductor L and its parasitic resistance RL. And for the switch network, we use a pair of MOSFET and a diode to implement the single pole double throw switch. And of course, we have the filtering cap. And the load resistor R. Output board voltage is marked as V. So for this switch network, we denote the transistor as Q. And we denote the diode as D. So if we look at the MOSFET, which is a fully controlled active device. So when we turn on the MOSFET, there will be a on resistance, which will incur conduction loss, right? So this is on state. And for the off state, meaning that we remove the controlling signal for MOSFET, we consider the MOSFET is an ideal open circuit. And for the diode, which is slightly different from MOSFET, so diode is not fully controlled, right? It's kind of semi-active device. In the on state, the diode will also have a conduction loss induced by parasitic diode resistance. And besides this, we also have a voltage drop incurred from the diode. So we use a voltage source to denote and this voltage drop. Usually for PIN diode, this could be 0.7 volt, right? For Schottky diode, this could be 0.4 volt. And for the off state of diode, we also consider its ideal open circuit. So both the R-on, RD, and the VD will incur losses in the circuit operation. Now let's consider those non-idealities into the boost modeling. So similar as what we did before, we consider the mode 1 and mode 2 one by one. So first, operation mode 1. For operation mode 1, which happens from 0 to DTS, the Q is on, right? Q is on, D is off. So we can plot its equivalent circuit correspondingly. Input source VG, L, RL. So Q is replaced by a on resistance. Diode is off. So here is the R on. C, R, output voltage V. So we can mark the inductor voltage, inductor current I, capacitor current IC, and try to write the expression for inductor voltage and the capacitor current. First, we look at inductor voltage. So VL, which is time varying, so equals to, based on the KVL in this loop, we can express it VG minus voltage drop across RL, which is IT times RL, minus voltage drop across RL. Then we can combine those two parts by extracting the common I, right? And also apply the small ripple approximation. Consider I is DC quantity. So this equals to VG minus capital I RL plus R on. That is the inductor voltage equation. Next will be capacitor charge equation, capacitor current equation. So IC, based on KCL in this node, right, equals to minus VT over R. Small ripple approximation equals to V over R. That is the capacitor current equation in mode 1. So next, let's look at what happens in mode 2. In mode 2, the MOSFET is turned off. So the current of inductor should be continuous. Therefore, the current finds a path through the diode to continue flowing. So we can plot the equivalent circuit. The mode 2 happens from DTS to TS. So for mode 2, we have input source L, R, L. So the diode is conducting. We replace the diode by this VD and RD. Capacitor. Load resistance R. And output port voltage B. So again, we mark those three quantities like inductor voltage, inductor current, and capacitor current. So based on this equivalent circuit, we can express inductor voltage and capacitor current correspondingly. First, look at the VL. Based on KVL, so VLT equals to input source. So we apply small ripple approximation directly here. So I just write capital I here. So minus voltage drop across this resistor, and minus VD minus voltage drop here, and minus output port voltage. So that's the inductor voltage equation. Next, the capacitor current equation. So based on KCL in this node, so equals to the subtraction of inductor current and resistor current. Based on small ripple approximation, right? This is capital I minus capital V over R. So we have fully expressed mode 1 and mode 2 separately. Next, we do the average and apply volt-second balance principle and the charge balance principle. So first, volt-second balance. So we average the inductor voltage in mode 1 and mode 2. So we will have average VL equals to D parts of VL in mode 1. Plus every D prime part of the value in mode 2. So we can break the bracket and combine the common items together, right? So we can simplify the expression. See that D plus D prime equals to 1, right? So we'll have VG. Similarly, D IRL, D prime IRL can be combined. The rest part can be written separately. So minus IR on D. And here, right, minus D prime VD. And here, this one. And this one. So the volt-second balance tells us that this quantity equals to 0. So we denote this equation as equation star. And next, let's look at the capacitor charge balance. So which means that the average capacitor current over one switching period at steady state equals to 0. So the average value equals to D times this expression plus D prime times this expression. So this equals to 0 at steady state. So similarly, we also break the bracket and combine. So this D prime combined equals to 1, right? So we can simplify the expression. So D prime I minus V over R equals to 0. And this is marked as equation double star. Now let's erase the blackboard. Okay, we have wiped the last screen. So now let's try to process those two equations we obtained. So first is the equation star, which is the Vg minus IR L minus IR on minus D prime Vd minus ID prime Rd minus D prime V equals to 0. So this is the equation star. Similarly as what we did before, so we can use a circuit to represent this equation. So we can construct the circuit model based on the expression here. So Vg is same as a voltage source. So IRL is a resistor. And the current is noted as I. This quantity is a resistor whose resistance is D times Ron. This one is an independent voltage source. D prime VD. This will be a resistor whose resistance equals to D prime RD. Finally, this will be a voltage-controlled voltage source. So the value here is D prime V. We close loop. So we can see that this circuit is equivalent to this equation. Next, let's process the equation double star we derived in the last screen. So I will rewrite the equation double star. D prime I minus V over R equals to 0. Based on this equation, we can also construct a circuit. So here, D prime I can be modeled by a current-controlled current source. So we plot controlled current source accordingly. And this will be a resistor behavior. The resistance equals to the load resistance R. Again, we mark the output current as V over R. So we can put those two equivalent circuits together as what we did previously, right? So I will replot this primary side and secondary side and put those two control sources in adjacent. RL, VG, D Ron, D prime VD, D prime RD, D prime V. And here, control the current source, D prime I, load resistor. So this is output voltage. And this current is V over R. This current is I. Okay, so if we look at this pair of control sources, so they can be modeled by a DC transformer model. So we can erase this part. And use a DC transformer model. Here is the coupling point, and this bar shows that it is a DC transformer model. And the turns ratio for this transformer model is D prime to 1. So we have established the accurate model for boost converter with semiconductor loss. And based on this circuit, we can try to derive the voltage conversion ratio. So we can express the output voltage based on the KVL loop of the primary side loop. So the output voltage equals to 1 over d prime times the subtraction of this source and this source, right? Vg minus d prime Vd times the voltage division ratio of those resistor network. So if we push the R to the primary side, then R will be equivalent to d prime square R. So we'll have d prime square R in the numerator, and denominator will equals to summation of this, and this. Plus d R on plus d prime R d. So this equation only contains the output voltage and the input voltage. So therefore, we can calculate the voltage conversion ratio expression of MD equals to V over Vg, right? So equals to 1 over d prime times. So this part is changed to 1, right? Minus d prime Vd over input voltage. And next will be this part. We divided both numerator and denominator by d prime square R. So this is 1. This is 1 plus RL plus dR on plus d prime RD over d prime square R. So this is the expression for the voltage conversion ratio. And similarly, we can also analyze the conversion efficiency. So the input port power equals to input port voltage times input port current. And the output port power equals to output port voltage times output port current, which is d prime I. So voltage times d prime I. Again, the efficiency equals to the ratio of P out over P in. So P out, P in. See, the I is cancelled. So this equals to V over Vg d prime, where the V over Vg equals to voltage conversion ratio. And we can substitute MD by this quantity. Interestingly is that the D prime can also be cancelled. So this part will be the final expression for conversion efficiency. And also we can get some hints based on the expression of efficiency. So basically, if we want to achieve a high conversion efficiency, it means that we should have this quantity as small as possible, much smaller than 1. And also, this quantity should be as small as possible, right? Meaning that the denominator should be much higher than the numerator. Much bigger than R. So those can give us design guidelines on how to better design a converter. Okay. So as we can see that the voltage drop on diode VD, MOSFET on resistance, diode on resistance, and inductor on resistance, those non-ideality features can degrade both the voltage conversion ratio and the conversion efficiency. In summary, the DC transformer model can help us to achieve the expression for voltage conversion ratio and efficiency. So those expressions can give us a quantitative guidance on how to better design our circuit.